Okay, it is being recorded from this side. In case if anyone is not recording it, I will have it and I'll send that to Abby later as in, and then you'll get it eventually. So today we'll be covering linear regression. I'm starting all over again, just like for recording purpose, linear regression principle and practices. And this is a very important topic simply because what we are learning here will also be applying to all different kinds of predictive modeling, machine learning, deep learning, and all that. And understanding the basic principles is the intent of this lecture. And I also talk about the exams last, the ones that we had yesterday had 4 questions, and most of them are subjectives. And the subjective questions can have wide range of responses. And as you know very well, it may not really have the right and wrong answer. It all just requires your thinking process and how to really just like take care of business when it comes to leading an organization, how you're gonna be doing that, what kinds of focus you are going to give, what are the resources that you are going to put your hands on, how are you going to leverage the 3 T's, which includes a technique, a talent, and also the bunch of other stuffs as well that we discussed. There's all different kinds of choices that you can have, and you can really just like elaborate it in all different kinds of ways. So I have received some responses, and if you definitely have, you can send that my way or Abby's way. But the intent is just to have you some kind of exercise. So anyway, we're gonna continue with this lecture. And in this one, we'll cover about the definition, equations, variables, features, oil estimation, assumptions, running the regressions, and also touch-based diagnostic features. And at the end, we'll have demonstration using Python. And as we will see, this particular technique is so fundamental. It is considered to be just like some of the most critical element we'll talk about. So what is a regression, a linear regression? It is a supervised learning modeling technique. We yesterday talked about what supervised learning is all about. You need to have input and output, or dependent or independent variable. And it is all about establishing relationship. The relationship can be one-to-one, one-to-many, and these will be described as simple and multiple linear regression. For demonstration purpose, we'll only focus on the simple linear regression because we'd like to really just show you how to do some of the machine learning techniques using linear regression. And once you know how to do it with simple data, it is a matter of just simply adopting the same technique to various kinds of modeling practices. It is the most popular technique among data scientists for both beginners and experienced. It's very intuitive with wide range of application. And what it does identify major drivers. And major drivers mean you can throw all different kinds of independent variables and find out those that are really impacting the dependent variables, right? And also you'll be able to see the predictors, how strong they are, what direction they are really just like pointing at. And of course, you can also do some kinds of forecasting, for not really in a sense of forecasting the future, but somehow you can say what would happen to my dependent variable if I manipulate the independent variables. So this regression in data science is done in quite extensive ways for market mix modeling, price optimization, demand analysis, risk analysis, and many more. So it's really very versatile. And it is typically called the Swiss knife, or the go-to method, or the ubiquitous tool of analytics in many firms. And if you have to have any kind of discussion about analytics, oftentimes regression comes as a top. Many leaders are also very comfortable and understand what it is and how it's being done. So it's really just very essential to really start that and advanced. I was actually hoping and planning to also add some kinds of clustering or decision tree for today's session. However, because of the time constraint, it's I found out that it's not really possible for this. And trust me, you can spend the entire semester just learning about linear regression. I have taken a linear regression 3-credit course when I was at University of Wisconsin-Madison. It's a 1-semester course. I've taken another course on categorical data analysis, which is basically talking about a logit model. Chi-square and stuff is 1-semester course. So just like this one definitely is very, very wide topic. However, we try to really cover it within the time that we have. So this is very critically, very important modeling technique, and you need to really be very comfortable about it. What are the features? How am I going to doing it? How am I going to interpreting it? And that kind of stuff. So, and also remember that this technique can be used properly or can also be abused. Especially, it is very finicky, very demanding. There are some kinds of basic assumptions, and those need to be fulfilled. We'll just examine them. And lots of the, I'm sure lots of you know this one here. I'm just bringing it to refresh your memories. That's the purpose and intent of this lecture. So just like any other thing, you need to really follow best practices of model building, validation, deployment. These are critical, and asking the right kind of question, assembling the right kind of data, doing quite lots of pre-processing. Last time we covered that about 80% of your work should really focus on data management, data manipulation, massaging, and so on, to make sure that you have the right content, amount, size data thrown into your model. And then, of course, you need to really select the right kind of method. So the linear regression is divided into simple and multiple. And simple regression is one-to-one relationship, and multiple, of course, is one-to-many. And there are several kinds of regressions: quantized, lasso, polynomial, and nonlinear, and so on. Each of them serve different purpose. And these days, also, there is what we call ensemble learning, or just like when you are running regression, lots of people would go into this regularization technique, which we don't have time to cover it. Regularization method is how can you improve the predictive power of your regression. And this is just all about reducing the error or the discrepancy between the predicted and the actual values, right? And that's an additional thing that you need to really just like embrace eventually. So linear regression is nothing but expressed in this simple term where you have got a dependent variable and y, and you have got the intercept and the slope, and you can have also, if you have multiple linear regressions, you can have several x2, x3, x4. And one particular unique feature about this one here, there's also this an error term or random error term embedded in this equation. And this is actually the salient and the most important feature of the linear regression. We'll describe that one, especially when we're talking about assumptions. Most of the assumptions is all about this particular error term. So as you know very well, it can be described as y regress against x, the dependent variable on this axis, and the independent variable on this axis, and you can write the graph there. So if you, now it's important how you are going to interpret that, right? There are two ways you interpret it. One is if your independent variable, in this particular case, we have unit as dependent and price as independent. You can tell the size and the direction of relationship. And the way how you interpret this one here is that for every unit of x change, the y will change by 5. In this particular case, it is positive. So if I change x by 1, correspondingly, y will change by 5. So it's very straightforward interpretation. And you might also have a data where your dependent variable is not really kind of continuous variable, but might be some sort of categorical variable, which is described in this binomial data, where one is there is promotion, the other one is not, there is no promotion. How you interpret this one here? When the way how to interpret is not the same as the one that we had for continuous variable, but will be based on the assumption that you have some kinds of base. Base typically would be the 0 or 1. So this particular value is telling you that if you are switching from 0 to 1, which is your independent variable, the change that you will be encountering in y will be this amount. So it's not like a 1 unit change, but this one is just like a change from the base to the other one. Typically, you select what the base is, and oftentimes the one that is not really just the most interesting piece is the base typically. Like for instance, this one is like if it is election or no election, you'll make no election as 0, the election winner as 1, and you interpret it accordingly, okay? So linear regression has many different kind of names. The dependent variable can be called to responding endogenous, especially if talking about economists. Oftentimes they call it endogenous, so it's kind of fancy name. But also in machine learning, they call it observed response variable. But there's a bunch of other outcomes as well. And also the x's can be called explanatory variables, exposure variable, exogenous variables. All of this means nothing but all the x's or the independent variables. So there are different, beware that there are different kinds of ways that you can describe the dependent and the independent variables. All right, So the beauty of linear regression is simplicity and ease of understanding. However, within it, many of the modeling techniques are embedded. You will be able to see interactions. You will be able to see collinearity diagnosis. You will be able to see quite lots of features that you need to really take care of before really start any kind of interpretation. So if you go further and do all different kinds of modeling, like logist model, nonlinear model, using any kinds of neural net, the same principle applies. So it's really nice to really just have a very well-grounded understanding of these the options, the features, and all that. So this linear regression is simplest family functions. It's all about constant rate of change. And this constant rate of change can be demonstrated using various kinds of real-world cases. A car travels from Addis Ababa to Harar at a constant speed from point A to Orbi. Or a swimming pool fills water at a constant rate. So this constant rate, fixed rate of change, equal change over equal interval, firm, steady, regular. These are really terms that are really appropriate to characterize linear regression. Is a real-world function like that? Perhaps not always. If you are trying to look at the way how a price is changing, unit is changing in response to price, you may justify using some kind of linear regression. You might also say, no, my units or demand may not really be expressed very well by price. So there are some elements that makes you question its utility, but for the most part, it is very robust and can really just do quite lots of good stuff. Linear regression has got 2 parameters, just like any other models. Every model has a parameter. These parameters are the ones that will really characterize, describe the interaction. Remember, all this is about establishing reaction, right? Establishing relationships. So Y is output, input, and B is the slope, and the slope is the rate of change. It is from our algebra class, vertical change over horizontal change. You can really just see this one here. When you are moving from here to here, that particular slope can be described as 2y2 minus y1 and x2 minus x1. And when you are dividing this one by this, you'll get the slope, right? It is the average rate of change. This slope will be the same. The rate of change at this point and any point on the line are the same. So the value of this slope is very important. And the value can range from it's infinity plus or minus from 0. So there are two characteristics on the way how this slope changes. Larger value means larger rate of change. The slope will be like this, and smaller value means the rate of change is slow, like the way how it is described in here. The other piece is also, there is also a direction component to it. It could be positive, which means the rate of change, or it is an increasing function. It can also be negative, that means the rate of change or the function is decreasing. And when you are looking at all different kinds of relationships, they can assume like a very strict, like relationship being one. This actually is correlation showing up. Linear regression and correlation are very related. It's all about establishing relationship, and there are different kinds of formulas that would establish how they relate. Like when you are having these kinds of trend, that means very strong positive relation, and this one on the extreme is negative relationship. And you might also have certain cases where relationships are kind of, assume different kinds of shapes, and there is not really any kind of relationship, right? Like if you try to develop some regression for this data distribution of this nature, you would end up something that is really kind of flat. It's not necessarily has to be the one described in here, but it could assume all these different kinds of distribution patterns. And yesterday we talked about distributions, very, very important. And so the way how it is you have got, this is very simple, but very important one. And you have got the y, the x, and you have got the OLS, ordinary least square. There is an observer mean, and that's the line. And y, that's the error, the observer minus any discrepancy between the two is what we call the error, the residual or the error term. So the intent of any linear regression is to minimize the sum square of the residuals. So this thing will wiggle around right, left, and eventually it will fix it somewhere where it is minimizing this particular value. So that is what we call this OLS regression, ordinary least square regression. So every modeling technique has its own estimation technique, and this one is the one which is really popular. Okay. So there are certain assumptions. I think there are 6 very important assumptions that you should always think about when you are running these kinds of model. The first one is there is a linear relationship between y and your independent variables. And this assumption must not really be violated when you are really doing any kind of this model. Visual analysis will tell you where you should really just are in terms of like this kind of relationship. The dependent variable, which is your x, must always be continuous. You cannot use categorical variables, so that's a big no-no. The error term and the remaining assumptions are all about the error term. Like I said, the error term in regression is very important. And the first is the error term do not vary with x, which means it's not really correlated with x. So whether x increases or decreases, the error term, when you are really graphing it, you should not really show any kind of trend. The variance of the error is the same for all x's, and this is really critical. You should really have some kinds of distribution like this, the one that is on the left, when you're already graphing this one here, doing some kinds of visual analysis, you should not really see any kinds of like bow tie or fan kinds of distribution. And there can be all different kinds of the error term being distributed this way. So this homoscedastic assumption is that the error term has to have really a fairly good distribution when you are really graphing the error against your independent variables. And the other patterns of distribution indication that there is some issue with the model, or maybe there is some kinds of violation made. And the other one is about different observations that you have or different kinds of rows. So the error term for one should not really be related with the next row and so on. That means that when one increases, the other one should not really increase. It should be random. And of course, the last one is the error term has to have normal distribution. And one of the diagnostic features that you do in this regression, and which is also true for many models, is that you would have lots of visual analysis or model outputs. And most of model packages have got visual analysis embedded in them. And you need to really just like leverage their uses. They are very powerful and will tell you whether what you have developed is sensible or whether you have violated some kinds of assumptions. Just like we have discussed earlier, all important best practices must always be implemented. You need to have like, this is just like what you should really do if you are really gonna be running some kinds of Python or R or SAS or any whatever. Actually, even you can run regression using Excel. It's very ubiquitous, very powerful, and very intuitive to just use it. As long as you're not really violating the assumptions, as long as you really just like understand what its purpose is. It has got limitations simply because in the real world, things are not really just like related linearly. That's why the neural network is becoming increasingly very popular, because the first thing that it does is it establishes the relationship as nonlinear function. And then from that point on, it optimizes and gives you all different kinds of improved predictive power. So these are some of the things that you would do if you are really running any kinds of analysis using any of the tools. We don't have to go through the details in here. We'll find out at the end. So the other thing is that there are quite lots of features or diagnostic features that you need to take care of in regression. And this includes the error, the model coefficient, the partitioning, R square, log likelihood, AIC and BIC standard. We'll examine some of them, maybe most of them in here very quick. But there are quite lots of things that you need to do about the distribution, about the strengths of the relationship, about the assumptions, the error, and the error is very important. So there's quite lots of stuff, and you need to take care of this. The output that is provided at the end when we demonstrate with Python will take care of all these things, and you should be able to interpret and then be able to assess it properly. So the assumptions, some of them are going to be just like this one here. One is like, I'm going to be going through what we indicated in here one by one, and we'll just like see how we are going to really bring all the information together. So far, so good. Any question? Is everybody okay? Oh, Daniel, that is so kind and nice and generous of you. Thank you so much. I'm very happy that you like the discussions. Wonderful, wonderful. I will definitely continue involved with this great, wonderful program, GOHI. and it is an honor and lifetime opportunity for me to be with you guys. Thank you for great. So we'll continue with this one here, and let's just like go one by one after I drink my coffees. Hi, Abby, are you saying something?
No. I was just everything is okay. I was just trying to say that.
Are you drinking your coffee?
Not really. Sorry for joining late. My internet is very bad.
So I'm recording from this in. So if you need, I can send you the. I don't know how to send the file, but
the link will directly come to you when it's completed. It will directly come to you.
Yeah,
through your email.
Yeah, I'm recording it in my computer though, so it will be.
Oh, in your computer, not in a cloud.
Yeah.
I thought in a cloud. If it's in your computer, there may be an option, maybe to download it or to just send the link.
Okay. Okay, sure. All right, let's proceed with our discussion of these different features. So one of the feature is error partitioning. Error partitioning is so critical simply because that's where you really just find out whether your model is really functioning well or not. And this is part and parcel of many model. Virtually every model has to really just understand where the error come from and how is this the magnitude, the size of the error. And is my model reducing the error or it's not doing good job in impacting the error and so on. So it's really critical. So the intent of many models is to minimize the noise and to make your model prediction accurate and to get the unbiased estimate of parameters. And in this particular case, and you guys know about this one here. So this is a very classic example developed by Ronald Fisher, and what is it came from agricultural experiment, and you have always some kind of source of variation. And in this for regression, these are just a very simple regression. You have got the regression and the residual. The source of the error can be from the regression, and you have got the error from the residual, and you have got total. So since total will be divided in these two, and you have got something called degree of freedom. This is a way how you can take some wiggling room to make an error. There is some description about it. And then there is what we call the sum of square. We'll talk about what the sum of square means. It's not just like simply thrown in zero. There are some, like for regression, there is some way that you can compute it. For experimental designs of various kinds, there's also a way to compute it and so on. Once you get your sum of square, then you can divide the sum of square by the degree of freedom to get your mean square. Then once you get your mean square, you divide your regression mean square by the residual to get your computed F value. F is Fisher. And this computed value will be compared with tabulated value and then see whether significant at 0.05, 0.05 or 0.01 level, and then see if it is really working or not. And there is also like other piece of information I would have loved to share with you, the way how this P is computed. There's type 1, type 2 kind of errors. And typically when you are doing this one here is you are really computing that type 1 error. So let's just examine this partitioning of an error is so critical in regression. So you have got a demonstration for that in here. Here is what we call that we have observed, and then we run our regression and we have made prediction, right? So if I have to do price, unit against price, my unit will be the observed one, and the predicted value of that analysis will be my predicted value. So this is really important. Then the next critical step is computing the error. The error is just nothing but observed minus expected. Once I got my error, I can compute so many things. It's remember this very simple step, however very powerful. Then I can compute my squared error. Squared error is nothing but I subtract this from the predictor one, which is the error square for each of the observation. And I sum it up this one, and I'll call that one sum square of errors. And if I take the average of that, to be mean squared of error. And then the next step would be I will subtract the predictor value, this guy, from the average value of the mean and square it. And then I'll get mean square of regression. Sum square of regression. At the same time, also, if I take this average, it's mean square of regression. And then this will be the total sum of square is like if I subtract this one here, every point from its own overall mean, and then square it, it will be the total sum of squares. Then once this is really just like computed, it's very important to understand what that means. First, there is what you call sum square of errors. What it does is, suppose we have got this particular regression line, and it measures the discrepancy between each data point and that particular line that the OLS is making after minimizing the sum square of errors, right? So this discrepancy is an error that cannot be described by the model, right? So high value is telling you it's their poor fit, and the lower it is, it's a good fit. So you compute this one, and you call this one here the sum square of errors, just like what we saw in this particular here, sum square of errors. If you average it, it becomes square of error. And you have got what you call sum square of regression, and this one is the predictor value. Is subtracted from the average. There's always an average, and you sum it up. And it measures how well predictor line fits data. And it's really very, very critical to have it done, because it will help you compute the R square and so on. And then when you are summing sum square of your error and sum square of residuals, it basically gives you the total sum square. When you are looking at it from this side, it doesn't really just make sense. But what this one does is basically what you see in this picture. This one is just simply gives you some value. However, that value, if you sum this guy and this guy, it will be the total sum of square. And that is already described in the equation in here. These equations are nothing but the one that was computed for this guy, and then you end up in getting this one. So this is really critical. Now, partitioning of an error is critical because you would be able to know where the source comes, how well your model is fitting, and so on. So this is what we have already described whenever we're talking about ANOVA is all about partitioning. For simple linear regression, you have got the regression residual, and everything is just like what I have already described. And also some of them are also included in here in this write-up. So nothing is really new. All right, so once you have this one here, then you are really just be able to do R square. Like R square is very important because it tells you the strengths of your model predictive power. It tells you how well the variability in your dependent variable can be explained by the independent variable. And there's also, I think this one should probably come later on, but R square is nothing but what we have already computed. We have computed the sum square of residuals and total sum squares. It tells you the portion of variability that is really described by the regression compared to the total variability. And you can compute it like this one here. And when you have many variables thrown into the model for multiple linear regression, you can also compute the adjusted R square in a slightly different way by subtracting this one, the sum square of error by total sum square from 1, and you'll get that value. So the value of the R square ranges from 0 to 1 because it's always squared. And the 0 means the variability in your dependent variable is not really explained at all by your independent variable. And R squared equals 1 is that variance is well explained, and the higher is always the better, right? And when you are taking the square root of this one, you'll find what you call correlation coefficient. And correlation coefficient is also has its own formula. I'm sure you know all this one here from your Stat 101 class. I'm not going to really bog you down on you to understand the formula, but just understand what it is. Correlation coefficient actually ranges from -1 to 1. What is this one here? Definitely, but there is some typographical error in here. So this is the proportion of the variance in Y that is predictable from the X, and these are what they call them covariance and so on. But at the end of the day, you will be able to really just like compute this one here and leverage that to really characterize the strengths of the relationship between your dependent and independent variables and be able to really interpret it properly. So this is really one of the outcome of error partitioning in regression model. And this is just like among many of the features that you need to really just like focus on. All right. There is also what they call the log likelihood. And we'll all see this one here when I'm demonstrating that in Python. So the way how the way how this one here and computing this one here is that is the OLS, and the OLS is very critical. So this one actually is just like parallel that you do typically in the logit model. This is a very critical stuff. However, you can get this output for linear regression in your Python and be aware of what it means. So the higher the value is the better of the estimation, and it is to really just like use to compare different kinds of estimation. Like for instance, if you have got 2, 3, 4, 5 different kinds of models, and in the first one you might have one dependent variable, in the second one you add an additional one, and if you want to compare them side by side, and if you have to really choose which one is the best one, you choose the one with the highest value. So its utility is about really just like using it to really compare and make the selection among different models. And you always get these kinds of value coming out in your output. And we don't want really have to go through the way how it is really being computed. That's just like mathematically, just a little bit beyond the scope of our class. But just be aware that this is really one of the features that you need to really take into account when you are really comparing different kinds of model for their robustness, for their predictive power, and what have you. There's also what they call it AIC and BIC. AIC stands for Akaike Information Criterion. This is named after the person who coined this particular technique. There's a formula here provided. So it is all about the balance between a good fit and over complexity of a model. Sometimes people would probably throw so many of variables to enhance the predictive power of the model, because when you are adding so many variables into your model, your R square value got better and better and better. And like we said yesterday, that would probably be a very good indication of something what we call overfitting, right? When you have overfitting, what happens is that your model is learning the error as well as the signal very well, and it would be very poor in generalizing. Or when you are using that model using some unknown data or some kinds of test data, you don't really get very strong predictive power. So in order to really just like balance that, understand that one, you can use this AIC and BIC. And it penalizes complexity less, it penalizes complexity, and oftentimes you need to really just like select the values that are the ones that are really just like the lowest, but there's not really any threshold, okay, 150 or something, everything kind of relative. Like you might probably be throwing different kinds of variables into the model. So basically you would be content and happy with the one that is giving you the lowest values of this one here. So it's kind of subjective, but definitely there's value upon which you can really just base your selection. When I'm saying subjective, there's not really one definite value. You would say, okay, if this is going up beyond this point, or if it's going down beyond this point, that is the one that I will be adhering to. It's just like simple visual comparison of the numbers, and always you go for the lowest value. And of course, the standard error, the one tells you the spread of the variability of coefficients. We'll be able to see at the end what the output looks like. And then you have got also t-statistics, and you use the standard error to compute that one, and typically it is at 0.05 or 0.001 level. And you already know all different kinds of hypothesis testing and assumptions that go with it. And the other one is what we call multi-collinearity. This is really perhaps if you have to rank the importance of various diagnostic features of linear regression, this should perhaps be at the top. And always, always, always make sure that your variables are not correlated in whatsoever magnitude. The relationship can assume different kinds of ways. Like for instance, suppose I'm running some kind of regression, and this also works as well for many other models. So bear in mind that many of the things that we talk about here also holds true in other modeling scenarios as well. So suppose we are running a model where Y is our dependent and there's a bunch of independent variables or predictors. And these predictors can relate in multiple ways. One, X can be related to X2, X also can also be related to X3, and so on. X1 might also be related to this, to this, to this. It's just like the possibility, the combination is quite a lot. So when you are doing any kind of regression or modeling, you make sure that there is no relationship among these guys. They don't really relate to each other. Otherwise, you are kind of double counting or throwing the same kind of spice, taste the same, smell the same, throwing into your stew and hoping the stew will be changing. It's not going to happen that one. You got to make sure that you only add the spice if it's going to add some kinds of flavor or it's going to add some kind of value into it. So this multi-collinearity diagnosis, there are different ways that you can diagnose this. One is the VIF, called variance inflation factor. And so when you have got multi-collinearity, so many weird things would happen to your model. One is it will reduce the statistical significance of the independent variables, and the precision of the coefficients will be compromised, and the p-values that you are getting will be unreliable. So you got to be really careful and need to take care of that. So the variance inflation factor identifies the presence and the strengths of multi-collinearity, and it shows you how much the variance of a coefficient increases if predictors are correlated. That's what it's doing. So how do you compute that? It's computed as 1 divided by 1 minus r square. And you'll have quite lots of r square being computed. We'll show you how it is really done, but you don't have to do it in the background. It's being done for you, and it gives you that VIF value. And typically, the value 1 is not correlated to 1 to 5 is reasonable. Most people will be happy to get value, VIF value of 1, 2, or 3, and they can live with it. But if the value is higher, sometimes even can go like over 10 and stuff, or anything greater than 5 is a very good indication that your independent variables are highly correlated. So you have to really just like make sure that you reduce your VIF down to like around 1, 2, perhaps 3, but not really more than that, okay? So the way how this VIF computed is that you remember what we talk about R square? What R square tells you? R square tells you that how that particular dependent variable is, its variability is described by the independent variables, right? So you would be computing many, like for instance, many kinds of R squares. Just by forgetting the dependent variable, you will compute how this guy X1 is related with the others, and X1 becomes the dependent variable. These guys become independent variable, and you compute R square, right? And then next time you go the next iteration, you assume X2 is the Y, and the other ones are the X's, and you run another R square. And you continue doing that one for each one of these guys. Each one of them will have a chance to become dependent variable, and the remaining ones become independent. You run it, many R square. So the value, like for instance, you get value from 0.1. Like for instance, if you are getting 0.1, your VIF will be 1.1. R square value of 0.1 is not really that high, right? So you'll get for each of the X1s, you'll get separate VIF. And the way how you compute for that one is by just like running some regression under. You don't have to see it. This guy against this Y and compute R square for that one. So this one will have got one VIF, and the values are this. If it is a if the VIF is 1.1, that means R square is 0.1, which is really low. That means this guy is not related with this guy. If this guy has got a value, R square value of 0.5, that means the strength of this relationship with the remaining one is 0.5. That VIF value becomes 2. Here, when you are plugging 0.5 in here, this is what you are getting. The moment you are getting very strong relationship, that is say 0.8, when you are relating this guy with the remaining one, your VIF becomes 5. This is where you say, no, this is really too high, because this guy has got strong relationship with this guy. And of course, the higher you go, your VIF can be just like huge. And these are boundaries that you say, no, I don't want to have anything. I don't want this guy have any kind of relationship with this. I would like to have this guy a very small R square value with all, which is in the area of 0.1, 0.2 or less. And that's how you are going to be using. The reason why I'm really dwelling in this one a lot is because it's very important. And many people disregard this and simply run without really checking the VIF, and then voila, they got the results. But when you are peeling the onion, you will definitely see some kinds of issue with that. The other diagnostic feature is what you call autocorrelation. Autocorrelation, like I said earlier, is whether this particular value is related with the next one, whether this one related. That need to be avoided, and there are techniques to do that, and that is what we call the serial correlation, autovariance, sometimes they call it. And this is typically very important in time series data, because time series data typically, if you have got bigger cell, Yes, last week you might probably have bigger, maybe it's around like holiday season, or there might be new store opening, or you name it, there might be all kinds of reasons, right? So you need to really just like take care of that. And there is a technique, what they call Durbin-Watson test, DW. And the way you compute that is indicated in here, and a value around 2 is good. That means no autocorrelation. But if the value is below, far below 2 or far higher than 2, there will be some kinds of negative or positive autocorrelation. Positive autocorrelation means when what happened in the past increases, what will happen today increases, what will happen tomorrow increases as well. It should be a random thing. It should not really just like something that what happened today should not really depend on what happened in the past. Okay, so that is one very important thing. And as I said, it's very important, this one in time series data in forecasting, and in other ones may not really be that much important. Let's say this one, it's not as important as collinearity diagnosis, right? But it's something that you need to really take care of well. There's also in linear regression what they call skewness test, and this one is whether your particular value is skewing to the left or to the right. Interestingly, when something is skewing to the left, you think it is skewing negatively, because from the point 0, when it goes to the left, it is all negative, and to the right it's positive, but it's the reverse actually. When something is really huge on this one, you call it that one positively skewed. When something is, and all the tails are on the left side, and that one would be negatively skewed. And this relationship is also shown. This is very popular actually. I think the reference, I got it from here. You'll find it in many textbooks. And the value has to really just like be between 0.5, minus 0.5 to 0.5. And depending upon the kind of data that you are dealing. For instance, you might have sales where these big customers are doing huge volume of purchase, right? And you have got these small customers who are really just like not frequent shoppers. They only just buy sporadically. And when you are trying to look at the way how the purchasing pattern is among these customers, you'll see highly skewed values, like this kind of stuff. For instance, you might have, if you put the volume on this side, the volume on this side, the number of customers, you have got very few customers buying huge volume and so on. And this one has got implication on the way, the robustness of your model. So there is always nice to check that as your. So the other piece is, of course, you have like what they call omnibus, kurtosis, and a bunch of others. You'll see them. And I have provided some of the stuff in here. There is like, and also like, okay, there is what we call kurtosis test. And this is the pickedness or flatness of a curve. Is this important? Why should I have to worry about this? This actually has implications and uses, especially in the stock market, right? So in stock market, money change hands very quick. And oftentimes people would like to buy it low, their stock, and want to sell it when it is at its max. And when it's max, that means that's where you are getting lots of profit. But that one also depends. Some of them, they might be at their max there for a brief period of time, and some of them for reasonably good time, and some of them for extended period of time. So this means this guy, the platykurtic, has got so many wiggling room. You don't have to rush, sell, buy, blah, blah kind of stuff. So I read some interesting articles that lots of these stock traders use the pattern of this for their actions of purchase and selling. The other is Jarko-Bera test, not very popular in the mainstream analytics, even in this machine learning techniques, but it is an output that you find when you are running this regression. And it is all about the distribution. There's many things that you would find tells you something this or something there about the distribution, the nature of the data. And it's nice to be aware and cognizant of how to really just like use that one to really have clear understanding of what the data looks like. So in this particular case, a value far from zero is showing you that the data is deviating in distribution from the normal type. And there are lots of features that are attributable to this one here. You'll see it. There's also what they call condition number test. The smaller the value, the less the fluctuation. Tells you about the sensitivity of the function output into its input. You know what output and input is. It's another way of describing dependent and independent variable. So in an indirect way, it is telling you some kinds of multicollinearity, and the smaller the value, the less the fluctuation. There is numbers out there, and oftentimes this, without really making a comparison with another comparable test, it might probably be harder, but be aware what it is when you are looking at it in your output, okay? In addition to this, also we have this outlier detection. This very important to know, okay, what point is an outlier, right? Oftentimes you might have a distribution like this one here, where everything is hunky-dory, nice, wonderful, you don't have to worry about. But in life, things are not like that. You might have an observation down there, or you might have observation down there. How are you gonna detect and how are you gonna be managing that? There are techniques in regressions, and there's 3 of them actually. And one is called Cox-D, and the other one studentized residual and defeats. Like for instance, the studentized residual, its a value is greater than 2.5. That particular observation has got some issue. Some people might put it into 3 or 4. And typically, you can create some kind of automated code that goes in loop, and it does multiple regressions, and it's run first time around. It picks one based on the values that you set up for studentized residual, Cox-D, or defeats, and then it will eliminate. And then once that eliminate, it fits the regression with the remaining data. And again, it computes whatever you like to really check this one. And then when the threshold is passed, it removes 1 or 2 observations up until a point where you end up in getting observations where the value that you have selected, could be studentized or Cox-D or defeats, are not really greater than the threshold, where that threshold means there is not really an outlier. So outlier detection, outlier identification and management is a critical component to regression analysis. And this can also be used in many risk management models. I have used this approach a couple of times in the past, and it comes really very handy, very quick, robust, easy to understand, and also easy to communicate with consumers. Consumers means your managers or different teams that you are working with. Okay, that is what we have, and I tried to really proceed into Python demonstration to show you. And then we'll jump into, well, maybe let's just go first into, because I think today around I'm a little bit faster, which is really nice. And today is Friday, right? You need some kinds of time saved at the end, maybe five minutes or so. Let's answer questions and ask. Let's just check this one out. The first one is, Burhan's asked, I need more clarification on the concept of ordinary least square technique, and if possible, the concept of maximum likelihood estimation. What does they usually mean? Basic concept. So this is a very interesting question, Burhan. The OLS is the one that is used typically by this estimation of that line. The estimation of that line is very critical, right? How do you really just select the line that minimizes the square, the sum of the square of the residuals? So like in one of the things that we saw, like every every data point has got some kinds of distance from the line. So it just like play around, like see, it wiggles around up to a point where that particular value, which is the sum of the square of the residuals, is at its minimum. So if the sum, if that value is 10, and then next time around you compute, it becomes 11. Next time you compute, that becomes 8. It will lock it down and say, this is the one, the value with 8, because that is the minimum among many that are computed. So OLS is nothing but a technique of creating that particular line by minimizing the sum of the residual square. So this is very popular, and this is well entrenched. And oftentimes when you're talking about a linear regression, so they call it just OLS regression or OLS estimation. The maximum likelihood estimation is a little bit complicated, which means that it's not something that you can describe like in a term, in an easy term with like OLS. What it does is, like when you are running the model at the beginning, it will just say, it will just create some kinds of parameter. Okay, my slope is for this. Like for instance, if I'm running one simple linear regression, the slope for this one could arbitrarily be selected and then see how it fits. So it does this one here iteratively. So like if you have several kinds of independent variables, it will do it several iterations, and in your models, in your model, it will describe you, okay, your model in your log, you'll see that the maximum likelihood estimation did 20 or 25 iteration to estimate the slope or the parameters, and finally it would find one, and that one is the one that gives you good prediction, and it will say, okay, your model is convergent. And one of the things that you need to really check when you are running models is whether your model is converging or not. That means the algorithm have found a very good prediction, and that is the one that you are going to go to the finish line. And it's not uncommon also when you are running the model can fail to converge. That means because of the nature of the data or some features, you are not really getting what you are looking for. And then that means you have to go back and tweak your data and remove or modify some of the variables and enhance and make it better and rerun it and then see if your model converges. I hope that answers you better. So in the absence of face-to-face communication, I would just simply assume that at least it will answer about 50% of the questions. Okay, the next one is again, Burhan. What are the x-axis and y-axis for checking homoscedasticity assumption? Thank you. The homoscedasticity assumption is that you have got the error terms, the residuals. You can put the residuals against the x. But in regression, you can also do this one here against y as well, the predictor value, and then see whether, and typically the first thing that you would do, like if you are running with Minitab, with R, with SAS, you have got these kinds of several features, diagnostic features, visual features will tell you, okay, this one is behaving this way, that way. So basically, the more evenly distributed error terms, whether it is against X or Y, is the better one. And oftentimes that can be done, can be checked quickly. Is normality a must? And Baye is asking, is normality a must for linear regression? Yes, it is a must. However, life is not like that. Sometimes you can really just violate that assumption and run the regression, and you'll be fine. As long as that violation is not very serious, you can be really fine. Violating a little bit here and a little bit there is okay. You know what I'm saying? But theoretically, that assumption must really hold through those 5 or 6 assumptions: the homoscedasticity, the autocorrelation, the linearity assumptions, the dependent variable being continuous, and so on. Each of them need to be held really, the collinearity and stuff are very important assumptions. So it's like something that you need to take care of many aspects of the outcomes, the feature, in order to get valid. But violation of a little bit is okay. It's like kind of dad or mom when the kids are really making some mistakes. If they are making some mistakes, they can tolerate that too much. They will be, reprimanded seriously. Will be put out of playing games and that kind of stuff. So a little bit is fine. Abel is asking, should we worry about correlation between categorical covariates or for only continuous? For all of them, it doesn't just stops for only continuous variables. It also for categorical variables. The categorical variables are a challenge on regression analysis because you have got 1, 0, 0, 1, 0, 1, but they are categorical variables, right? And those things need to be examined. I have done so many of this one here, and oftentimes you'll get values of correlation when you are doing, like, for instance, in SAS, you can do some kind of procore, and then you'll be able to see the outputs. Maybe you might have 10, 20, 30 independent variables you'll be able to see. And some of the independent variables can be categorical, but the way how you are interpreting that correlation and stuff is similar. So if it is high, that means they are highly correlated. So yes, need to be taken care of. I think that is one way of really diagnosing multicollinearity. One quick and dirty and first way to do it. So anyway. Oh, this is Brian again. What if there is multicollinearity and what is multicollinearity? I'm telling you from experience, is a very, very, very important feature. Autocorrelation, I don't really worry about it that much. Of course, autocorrelation, like I said, is relevant to time series data because time component matters. Whether what you have today, what next time or before matters. But multicollinearity, trust me, this is the most important. If you are really stepping into some of the financial industries or any industries, the first thing that they are looking at your regression model is how is your multicollinearity? How is this VIF? There's also a bunch of other the eigenvalue and a bunch of stuff. I don't really go into them here, but that is what people care most about. When you are throwing anything into your model, first and foremost, you need to take care of that multicollinearity. You must make sure that one thing is not related with the other. And VIF, I think, would be a quick and dirty way to do that. And like I said, the lower the value is always great. And also in addition to VIF, you should also do this multicollinearity diagnostics. There's a matrix that's coming out. You have to really look that one. I don't have really included in here, but it's very, very important. I hope that answers you, Brian. And then Zalalem asked, thank you again. I have just one question regarding outliers. People, they fit a regression model with and without outliers to see their impact. If the change on the coefficients are negligible, they recommend to report the one with outliers. Does this make sense? Yes, it does make sense, Zalalem. However, outliers are very touchy and sensitive issue, right? Like in business world, right? An outlier is not something that you are going to get rid of simply because it is an indication of something. It is an indication, okay, it is, for instance, if you want to build some kinds of model about sales against whatever, that particular sale that the regression algorithm identified to be outlier may have significant impact or meaning to the business, right? It shows you that in certain areas and certain circumstances, say sales is skyrocketing kind of stuff. Yes, the algorithm think that's outlier, but you need to really just like take it carefully. Removing outliers are big no for many of the analysis. Some leaders, they don't want any outlier to be removed from the analysis, and nothing is wrong with that because, like I said, certain outliers are left untouched. And now the second question will be, so the implication of removing an outlier is where are you going to stop? Once you remove an outlier, then the next time you are running it, something will pop out to become an outlier. Like the one I mentioned, there are 3 ways that you can know using the studentized, the defeats, and the third one. And you remove one, then another time you recalibrate and run the regression, you might probably have 1 or 2 or 3 pops up. So once you are traveling that route, the question would be, when should I stop? So you have to be really careful about this one, the implication on the business as well as the implication on when to stop about it. Okay. I hope that answers the question, Zelalem. All right, then can you tell us more on ways of eliminating outliers? Shall we check all the time for the outliers? Like this is Manuyelet. No, yes, that's a good question. And the one I described, I think the 3 diagnostic features will help you tremendously. You need to look at the studentized value, and 3 of them that we have described. And the thing is, you need to run it and then look where is outlier showing up. In all of this also, visual analysis plays critical role. Yesterday, when you're talking about data analysis, 80% of your focus always be on the data understanding, visual analysis, pre-processing. That is where you will be able to answer many of the things before even jumping into the model. And the model should really account about 20% or 15% of your work. Lots of the sanity check, outlier check, and all the things can be taken care of in advance. However, if you are heading towards the model, of course, every modeling technique have got the various kinds of diagnostic features, and outlier, of course, is a concern, something that you need to really take care of. Some modeling techniques don't care about outlier. They can give you a good estimate with or without outlier, but regression is kind of finicky, very sensitive to outlier. You might probably be removing one outlier, and the graph that looks like this one here might go this way, just like tweaking that one. So you need to be aware of that. Regression in general, linear regression, is very sensitive to outliers. Thank you, Ahmed. Okay, there's a question. I have a question regarding variance inflation factor. What we will do if VIF is greater than 5? I mean, if there is multicollinearity between dependent variables, if they are affected each other, what measure should? So that is a great question, Ahmed. So what happens is that you compute that VIF, right? Just the way how I described. And a value that is low is the one that you always prefer. Around 2 is a good one, maybe 3, but don't go more than that, because I have shown clearly that when you have got a VIF value of 5, that means that particular value has got a R-square value of 80%, which is really a very good indication that that guy has got strong relationship with the other independent variables, right? So the way how it's being computed is clearly demonstrated. You forget about the Y, you focus only on the X's, right? And every time each of the X's becomes the dependent variable, then the other guys become independent variables, and you compute that R-square. If that particular R-square is in the 80% range, when you are computing the VIF, it becomes like around 5. So 5 is really a strong indication that your particular variable is highly correlated with the other one. So I always suggest to use like a VIF value of like 2, perhaps maybe 3, I don't know. But different business leaders have got a very strict requirement that you must have VIF under 2. That's it. They don't really accept anything greater than that, and you have to abide by that. And sometimes when you are facing that, you got to do it, and it's understandably, justifiably so, because it makes very good sense. All right, I think we need to proceed. Zelalem, as another question, autocorrelation makes sense in time series and the like data. Sometimes autocorrelation occurs in non-time series by coincidence. Is there anything that we can do on it? I think that one, you're absolutely right. Those things can happen, right? the observations, the first, second, third, they can have correlations, right? Look at that, what's in the statistics, and see if the value is greater than the other one, then because you'll get that value for each row, right? So when that value is greater than, if that is a big concern, you can remove that one and then run and then see how that autocorrelation is changing. I think that is the best approach. But again, that one also, you might also run the moment you do that one, you might also be affecting, removing something else. So all of the things is telling you that modeling is not just only throwing the numbers and getting the output and you are done. There's so many things that you need to retweak and understand, and back and forth, back and forth. That's why it's by its very nature it's iterative. So anyway, these are the questions that I got so far. I hope I try to answer this one here. And there's also a bunch of them. Let me just jump. Okay, I can probably add about 10 minutes if you bear with me. I'll be fine. My work begins at 8 and stuff. So I work from home at this point of time. So it comes very handy. And I attend lots of meetings and so on. Okay, all right. So in the chat, what we have gotten here is, let me address all of them. Okay, I love all of the comments. Thank you so much. Your kind orders, wonderful, goes a long way. Okay, Caleb asked, is multicollinearity applicable for categorical data? If not, what technique could be applicable in there? Yes, 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 this is big yes. Multicollinearity applies to everything. It doesn't matter whether the data is continuous or categorical. You got to really take care of that business before you really do interpretation of your data and stuff. So you have to make sure that all of the independent variables are nothing to do with each other. That way you have really just a clean slate and be able to really defend, be able to tell compelling stories. But if you are having some multicollinearity, it is kind of compromising your work. It's kind of presenting this nice, wonderful food with a plate which is not really clean. So you got to really take care of that, cleaning the plane first, which is multicollinearity. Like I said, first thing that you need to really take care of. And I have seen this in practice, and people will throw away what you produce unless you really just take care of multicollinearity very well. Thank you. I have a question regarding, and this is Ahmed again. Okay, this, I think we answered this one here, Ahmed. Rikin asked, yes, the nature of outcome variable doesn't matter being linear or logistic. Well, that is like one of the assumptions for linear regression is that you need to really check whether that relationship is linear, and lots of visual analysis will definitely help you. And sometimes if the relationship, when you do X versus Y, if the relationship is showing some, this very curvy or some kinds of like this one, you might probably to think of using another modeling technique than linear technique. Remember, linear technique has got shortcomings because in real world, many of the things in life are not really explained very well. So if you are savvy in modeling technique, the choice of logistic model, the choice of linear model oftentimes work. Of course, when you are stepping into nonlinear models, the work becomes more involved because you need to really set up the parameters and that kind of stuff. But you know, you always get the output that you are looking for. So I think you need to decide which model approach that you see based on the diagnosis and the pre-processing work that you are doing. Aha, you asked a very good question, Erkehun. And that is, you can use VIF for linear logistic, and you can use either VIF. Go for it. Yes, you can use VIF for logistic regression as well, because when you are doing logistic regression, you can use that VIF. It's kind of a little bit hidden trick, but you need that VIF because what VIF does is nothing but establishing relationship among the independent variables. Even if the model that you are building is logistic, I think that's a good approach. We use that one quite often for logistic regression as well, because we need to really take care of that multicollinearity. And I think VIF is known to be robust, simple, and intuitive. By asked, can I remove the outliers to fit the regression if there are outliers? Well, this is like the ones that we discuss a lot. There is always some touchy kind of points about outliers. You have to be careful. Some business leaders, data scientists don't want to touch outliers whatsoever because they might be telling some compelling story about the nature of the data, business, and so on. I think, but most of the decision has to be really just like up to you and your team. Up to percent up, and then Germau asked up to what percent of outlier or any misvalue are not affect the quality of data. Well, you need to look at those diagnostic features, the student size, t-value, and stuff. And you can't really fit it by removing one and then with others pop up. And sometimes you have to do 5, 6, 7, 8, iterative time. And every time something pops up, and then because you put some threshold in it and stuff like that. So outlier is very interesting, but you have to be really careful about it. So anyway, let's just go to the demonstration. The question and ask would be enough in here. And what I would be doing here is that let me have quick demonstration of the, and I need to really change I will change the presentation mode to just normal. Okay. And I'll go to the Python. All right, we'll just demonstrate this Python, and what I'm going to be doing as usual is copy what I have in here, go take a presentation. It's kind of takes time and stuff, but definitely I think it will work. So if I go share this one, I need to create additional this Python 3. That's where I will be running my Jupyter notebook. So I'll go back and forth. So let me just go to this PowerPoint and grab. First, I need to really bring this particular data, which is which is 100 lines of data and shows you invoice, price, and unit. Let's just like bring it, this one here into our Python in here, Jupyter notebook. And what I do is here, as I pasted it in here, let me put this one here on the corner. And if I run this Alt-Enter, this particular stuff is already here. I can use the easy one is this one, Alt-Enter. This is the data, what it looks like. And I can do just to look at what the distribution, the mean standard deviation of this data looks like. Has got 100 rows by 3 rows. The first row is invoice, units, and price. This is what we're going to be using. And I have some data, just this is fake data created for this particular purpose. Once I have this data, then I will go to my PowerPoint, we'll share with you, and grab some of the stuff in here. And the first thing that I would like to do is do some kinds of correlation. Maybe I can probably jump into bring the libraries first, and maybe that's a good idea. Let me just go. Where are you, library? Library is here, and there are 2 of them. This guy and this guy. Okay. I've got a bunch of libraries in here. I'm jumping to page 57 and bring all these guys here first. So that will save me time. And I will go to the Python here. I'll share you that. I bring all those libraries in here. and alt enter. Now I've got so many things coming here. I have got the pandas, numpy of different kinds of sub-libraries, including mean, standard deviation. This is the thing that you need to be aware when you are trying to do any kind of regression or something. You need to really know what are the libraries. There's quite lots of, like for instance, regression can be run using different kind of libraries. These are the ones that I chose, and some of them might be too much, but I use this one here quite often. I just simply put it in here. So once I have this guy, I will go also into my PowerPoint again, I'll share that with you, and I'll also bring another group of libraries as well, because this one was not able to be fit in the earlier one. And what I do is just go back to my Jupyter notebook, share that with you, and paste this one again. And I've got all the libraries that I need. And this one bring the matplotlib, numpy again, actually, maybe it's not necessary. There's also Seaborn. This is for the visualization purpose. You got to be aware of the power and the versatility of these kinds of libraries. And once I have this in, I'll go to my PowerPoint and let me just go upstairs in here. And first, let me do some kinds of correlation here. And I can't describe this to you, but what it does is very, very straightforward correlation analysis. I go to my Jupyter back and forth. And what it does, it brought, okay, it's just like compute the correlation. I named that particular library, I mean, data that I've imported. I showed you RD is regression data. I like to really name my data in a short kind of acronym. And I'm using the Seaborn library. It's very powerful. And give me some kind of heat map actually. And I can really manipulate the size and all that in here. All I have to do is alt enter, and I get this particular stuff. And this is really very powerful. So what's showing is that price units correlated with this one. And I've got a heat map by just looking at the way how this color is like. I can just look like the relationship is kind of in the area of negative, the correlation. Of course, we'll be able to also to see that one. So what I'm trying to emphasize here is that you need to do quite lots of analysis before you jump into your model, okay? Then I can go into the PowerPoint. I see my correlations, they are correlated negative. Actually, I do it in a very fancy way. And think about it, if you have got so many independent multiple linear regression, you can really see very nice heat map, shows you how one related to other, and so many of them. And I can also do some kinds of understanding of what is the distribution of these independent and dependent variables look like. Like I can use this script, for instance, to get what you have already seen in the PowerPoint, but it's just nothing fancy. It's just simply plotting the unit and gives me something like that one. So just by looking at this one here, I can see that the majority of the units are within 5 and 10 ranges. That's what the histogram is there. And there are some distribution to the higher end, but this is just like some visual understanding of what my units like, okay? But this can be done using Seaborn robustly for all of the variables at once as well. So make sure that you are really aware of that. Seaborn is very humongous, very powerful library. So I can do that for my unit. I can do that for my price. These are the two variables that I have. I just prefer a very simple one for demonstration purpose. And also, if I want to see some kinds of relationship, I can use these kinds of plotting technique. And what I'm doing here is copy this, bring it in here, and this, just like by doing this one here, I call this one here now, instead of like RD, I call RD2 because I would like to get rid of that invoice, the one categorical variable, and now I'm only keeping the unit and price, and that one is called now RD2. Now I'm saying, okay, please plot RD2 and give me something. So I alt enter. And this is just like the printing. First, I have asked it to print, and then I have asked it for the graph. So as you can see, as price goes up, and units goes down. That's what also the correlation told us. So this understanding is so critical because now I have really a feeling that what that data looks like, right? Just even before I go into my model, I know exactly what is going to happen. So first thing, what you can do is just simply simple linear regression without data splitting. Without splitting, simply throw everything and then look at it. I think that is what we traditionally do, right? And for that one, I can use this particular code. Look how powerful it is. Just one line of code gives me all this output because some very smart, intelligent, helpful person somewhere have written a library for me to have the luxury of leveraging it and got everything that we need. So lots of the diagnostic things that we have talked about last time are shown here. I have got the intercept, the price, the omnibus, the skewness, kurtosis. All I have to do is just simply look at this one here and interpret this one. So all of these guys, I have described it in the document. R square, adjusted R square, F statistic, probe, log likelihood, AIC, BIC, blah, blah, blah. All you need to know is done for you in a single script, and the interpretation is to it. So this is one approach, the way how we're doing it in the without really having to worry about, okay, what is my robustness of my model or something, right? And this is not really the best way. So the best way would be the next one. I will just show you. And this one is with data splitting into training and testing. So what this one does is, I have, like in this particular demonstration, I have 100 rows of data, right? My price and units. And what I'm going to be doing is split that one and develop the model on the training and then validate it on the test data. So I hope you guys are with me. We are taking a little bit over time, but it will go very quick and I won't take your time too much. So the first thing is I select variables and split data into training and testing. What this one does is, okay, say this guy is my independent one, and this one is my dependent one, which is unit. I set this one up, and then here I split data into test and train. I have to import these libraries. Actually, they are very important. I think I might have imported a portion of this one here in that big importation I showed you. And then these are very classic, very, very important. Sklearn is the one that is always used in many modeling techniques, logist model, and a bunch of others to split your data. And the splitting always follows these kinds of formats. So I set up in here, okay, my test size will be 0.3, and I don't have to specify my training. Of course, if it is this one is 0.3, the other one will be what? 0.7, right? If I put this one here, 0.4, the other one will be, of course, 0.6, which is 60% versus 40%. And I also say this one here puts my random state 0, and this is very important. If I put certain number, this thing will be fixed. So next time I run it, I'll get the same kind of result. But this time around, if I put a 0, next time around, the randomization will be new. And whichever way you want to do it, make sure that you are really using some number or zeros. Very, very important. So what I'm gonna be doing is I copy this guy and go to the share here and bring it in here and run it, right? And paste it in here and Alt Enter. Now I have got, if I print this one here, I can really just like see what they are. So I have 30% or 30 lines of code is assigned to the test. And now I'm going to develop model on my training data, and that one consists of 70 lines, 70% of the data. For demonstration purpose, like I said, I have put 100 lines of data. Then we can go to our PowerPoint here and get what we are looking for. And this one, okay, we have already done this one, the libraries, and this one also we have already done. We don't have to worry about it. And then simply run the model here. So actually the output are shown in here. Just for demonstration purpose, we can copy this guy and bring it into our Jupyter notebook, and either we run here or just simply Alt Enter And there is some issue. If it okay, well, okay. What happened here is that the library, I know how to fix this one. It shows this one requires this guy, I think, for some reason. This one needs to be run again before if I import this guy here, I can go here and simply run in this one. I'll be able to get the output. And these outputs are exactly what we have already seen in the PowerPoint. And all of the diagnostic feature for that model are shown, all of these guys here. And I have gotten this particular case, only the X1, and then you will ask, where is my intercept? Because always you have got y equals a plus bx, and this one is the b, or the slope for the X1 in this particular case. And for this particular case, you can go back to so we got all the information that we need. You might probably just go in here and compute the intercept here, just bringing this one. And with 19.4. So if you go to your PowerPoint, and this is the equation that you are getting. So we run this model, and we have got this equation 19.4 plus, this one should be minus 2.36 times price. This is your equation. So for every change in price, for every unit change in price, of course, unit will be going down by 2.36. That's a very straightforward interpretation. So this is what you do. This is, you are doing it on the training data. Now you want to see how this works on your test data, and that's the trick, and that's the goal of actually this presentation, right? So when you are scoring the model parameters on validation data, this is what you do. What you are doing is that, okay, get the parameters, the one that we have already seen here. This guy is 19.4, 2.36. Now, instead of feeding the data from the training, feed the data from the testing into the price, and then see what kinds of predictions that you are getting. That's all what you are doing. So whenever you are talking about scoring, it's all about using the parameters from the training, and then run your model and see what the predictive power is going to look like. So that's what I'm doing here. Y predicted, regressor predict X test, print out. I've said this one here, PD data frame, and then give me the printout. So this is so critical. This is you remember we have got 30 rows assigned to your training, and Python count starts from 0. And when you are seeing this, there's 30 observations. And here is the actual, and this is the one that is predicted. The prediction for this one, we use the parameters from the training data, the slope and the intercept, and plug it into this guy, and we are getting this one here. Now, is this one makes sense or not make sense? That is the holy grail of these machine learning approaches, especially the supervised learning, okay? So now I can go to my PowerPoint here. And I can do this one here. Okay, give me a graph. How is the predicted against actual looks like? The same kinds of stuff. I think this one looks like the information that we have seen using the entire data. But this one is just only using these guys. You're simply converting what you've seen here in the tabular format into some kinds of graph. And here you'll be able to see it. Yes, of course, this one reflects what we have already seen using the entire data. And there are two very important pieces that we need to do after this. And the first one is, okay, measure the accuracy of prediction. In this particular case, okay, what is the mean absolute error? What is mean squared of error? What is the root mean square of error? And also you can also add the R-square value for this one here. And as you know, the higher the R-square, of course, great prediction, and the lower this guy's value is always the better one. And when you are running this, guys, you will find this, what is shown in here. I can just simply do this one here very quick. And I guess this one here, I think root mean square of error is low. Anything lower than 5 is a very nice one, but definitely always emphasize the lower values. I would have taken half of this lecture to really describe all of the error computations, how they are being computed, how they be compared and stuff. But just bear in mind that always the lower the value, the better the predictive power of your model are. And you can take one additional step if you want to. And that one is to look at how the predicted value and the actual value and the predicted value looks like graphically. And that's just one of many ways that you can see how your prediction. So each one, this is the actual value for each of these 30 data pointers. Only shows the limited numbers in here, but if you tweak the graph in here, you can accumulate money. But definitely shows you that some of them have got a good match. You see these guys, some of them show some discrepancy. Some of them, they show really good prediction. Of course, there's noise and stuff. This one actually is performing really bad. And what this one is doing is basically just simply graphing these guys and in a visual format. So overall, this particular model works really well. Based on these values that we saw and a bunch of things, and we can say, well, we are really great. And since this is a very simple linear regression, it doesn't have lots of the diagnostic features that you're talking about, VIF and so on. However, from what we have already seen in here, we can be content and we'll be happy with our model. So that's all I have for today. And I cannot express my gratitude to GOHI leaders for giving me this wonderful opportunity to know you, to share with you what little I know. And I hope this will be just like the beginning. We'll continue enhancing these features, and next time we can use either R or different kinds of modeling technique depending upon the demand. But this exchange of knowledge is nothing but a capacity building effort, and lots of tips and tricks that we are using in here can also be used in many of the fields that we are using. So regression analysis, as I said, is simple, but it is a gate to many of the sophisticated models. Like if you want to be a full professor, first you have to be assistant professor, then you know, associate, and then full professor, right? If you want to become a 4-star general, you have to be what? You have to be commissioned officer, lieutenant, captain, major, lieutenant colonel, colonel, brigadier general, major general, the lieutenant general, and then 4-star general. And if you are lucky, you can become 5-star general that we don't have really for the past 50. I think the last time that we have 5-star generals were in the 1950s. There's only 4 of them in the US history. But anyway, to reach that one, you need to enter through the commissioned officer. And the same thing applies here. If you want to do sophisticated models and stuff, you need to go through the regression. It is the gate. There's no really way to go around it. So if you have mastered this one here, trust me, you'll be capable of doing many other great kind of modeling techniques, including all the way to deep learning, because the principles and practices that you are learning this one also held through in a different ways and different forms. So that is what we have. I think, Zelalem, you have a question. When we writing the fitted model, can we include the error term? It realized value. Thank you. Yeah, it's understood that when you are writing that equation, that error is already there. What you are, that equation is nothing but that OLS regression, the picture. is putting it into some form of readable format. So the presence of the error is very important. Like if you are taking some kinds of regression class, one of the simple and tricky questions that you ask your students is that, can you write the equation of the regression equation, right? And some of them, not all, but some, they forget about including the E at the end, because that's very, very important. Regression is all about that error term, and never underestimate its contribution. I think most of the assumptions are based on that error term. That error term is so critical to do predictive power, to do many of the things, because that tells you the discrepancy, how good you are really doing the job well. So, so when they don't really include that particular E, you penalize them a little bit. So next time they will remember that. All right, I have one more question, Burhan. Regarding the equation of the linear regression. In linear regression, there is an addition of error term residual, but not in logistic regression equation. If I'm not mistaken, after log transformation, the equation becomes linear, but does not have error term. In my reading, I did not get any answer why it is so. You say, yes, this is a very good question, Burhan. The logit model don't have error term, period. There is no really error term in logit model, because the way how that particular graph is computed is not like OLS, it's a different technique. However, in machine learning, some people, some data scientists are trying to come up with some kind of error term, and it becomes kind of controversial. And if you see that kind of output, always take it with a grain of salt. And lots of statisticians don't buy that one, because the logit model is like, an S kind of curve, and it is very dull, or kind of Siberia on the left side and the right side, nothing is going on. And this is rapid decreasing, lots of activity really happening at the middle. And each time you don't really deal with constant rate of change. The rate of change becomes at its max around the middle, and it increases at a decreasing rate, and so on. So you don't really have that error term that will really describe the equations there. But there are different ways that you can really just like assess how the model is working or not. Yeah, okay. I think that is all I have this one. And I would really be very happy if you have any question, reach me out. You have my address, and I'm really excited. And thanks again, GOHI, for giving me this wonderful opportunity. Dr. Wondosen, Dr. Gatenet, Dr. Desalegn, Abby, and the rest. It is an honor and a great luck to be associated with you. And thank you so much, all the students, for being with me and showing a great deal of interest.
Thank you very much, Doctor, for your nice presentations throughout the week.
Thank you so much, and take care. Have a great day. Bye-bye.
Bye.
Bye. Take care. Ciao.